We're starting off at the beginning of the session with a series of larger talks, and then we will move on to the early career scientists and shorter talks. So we're beginning with how to use the effective temperature as a new probe of stellar variability. And we got Zoomland up, looks like it.
So, hello, I hope you're all awake today, this morning. So I'll be discussing a paper that was published earlier this year that describes basically how you use, we can use temperature as an activity, basically monitoring tool. And so before we even get started, I have some background just so you see where I go with all this. So we all think of the effective temperature as a bulk property of an object, like its radius, its mass, and so on. And I'll be talking about differential effective temperature. So the very best absolute, and it's a little, I think it's important to distinguish between an absolute temperature and differences, because we will, as for velocities, we can get much better differential measurements as we can get absolute measurements. So the very best absolute temperatures are derived from interferometry, and combined with parallax and so on. We're having a bulk temperature, and here we'll be discussing differential measurement of the temperature. And I'll show you how we do that and how we got way better. So we'll be discussing differential temperatures and not absolute temperatures being things that you derive with interferometry, among other things. So first thing, I'll be discussing about velocities. I'll be discussing velocities just so you understand the concept. How do you measure the velocity of a spectrum? Well, you just wiggle it until it fits. No. It's fancier than that. What do? You say you have a template, you measure a velocity compared to something else. Okay. So you have a template, a very high signal to noise template, perfect template, another perfect, but let's say it's perfect. And you have your spectrum and spectrum with Spirou, for example. And you subtract the two and you say, I see some residuals. And how do you know the velocity of that observation? You basically do a dot product of these residuals against the derivative of your perfect template, of your template gradient there, and you can formalize that. It's basically a difference, and you just project against the derivative. So if you have no derivative, a flat spectrum is very bad for velocity because there's just no derivative. Okay? So you understand how we measure velocity. If there's no way to do in terms of information content, you cannot do better than that. Then you say, you could derive against any quantity. So you can take a little bit of a spectrum and say the captain's age or whatever, any quantity, you can have a derivative there and say, I get my derivative against the captain's age or whatever. So why not use in these other quantities temperature? So instead of having velocity space, we use a derivative in temperature. And basically you say my observation minus my median template of my favorite star. And you put a derivative, there's a CFHT but you see it's a temperature derivative at the bottom, and you find a variation of temperature for every single pixel or every single line, depending on how you build, in the spectrum. So you get thousands of temperature values, and you can do stats and get actually a mean change of the temperature. The best differential RV measurements, and so back to the RVs, today are done in the optical. They are the tens of centimeter per second accuracy. Do not believe anyone that claims anything absolute in velocities in astronomy better than 50 meters per second. So there's a factor easily 100 more than that between an absolute and a differential. And the very, very best stellar temperatures we can get have uncertainties at the 1020 Kelvin. How good can we get in differential temperatures? How do you define a temperature derivative? So that's not obvious for velocity. It's easy. It's a shift, and that's a velocity difference. So we compile a library of harps in the optical, Spirou, Spirou. In the infrared, objects from sunlight to TRAPPIST, so from M dwarfs to sun-like stars, and they were all reasonably slowly rotating. The rotation makes things messy here. Reasonably well-known temperature. You don't need to know the temperature of the stars very accurately because you're going to fit it against many stars and so on. So we made libraries, that's for HARPS, and you take one pixel, that central pixel at 632 something, and you say, that pixel, what happens to it? Well, it gets deeper and then shallower as you change temperature. So you can fit a polynomial. If you have a polynomial, you have the derivative of a polynomial. Therefore, you have a derivative of your temperature for that pixel, and you have it for the entire spectrum. So we did it for all objects. That's Spirou, and you get temperature derivative spectra. Okay, so if you change the star's temperature by 1 Kelvin, turn the knob, you get typically the values in the spectra are 10 minus 4, which means that you change by 100 Kelvin, you get order of a percent change in the spectrum locally. That's what we do. And say, espadon consideration, because you all know that we'll have a dual mount of espadon and Spirou. Will it matter? Because we're not stable at the meter per second. It will work because it's mostly a depth effect and not a centering effect. So even being unstable at reasonably stable, but not at the meter per second, then you're absolutely fine. There's no problem using espadon for this technique. We haven't done it yet, but we'll do it. So that's nice, but does it work? That's the wiki book. We try like the easy one, okay? The easy one. AUMIC, it's a young star. There's a really nice, these posters by NASA. It's star flares of fury. It has 3 planets, or 2 or 4, depending on who you ask. It's been monitored extensively with Spirou. And here's a time series for AUMIC. At the top is the effective temperature change. And you see the error bars there are actually correct. They are the order of 1 meter per second, 1 Kelvin in uncertainty. And you can pass a GP on that and basically see the temperature of AUMIC changing by a good 30 Kelvin at some epochs. And you say, and we have a spectropolarimeter, by the way, you know that. And you said, well, how does that temperature change match small-scale magnetic field? So it's not the same measurement at all. And they are super well anticorrelated. So the more magnetic field you have, the cooler AUMIC is, with a correlation of more than a minus 0.9. So we find the same period. So you would not need spectropolarimetry to see that rotation. But we have it, so we confirm that you can do it with any spectrograph. So that was an easy one. We tried one of the most quiet stars that we observed a lot with Spirou, Barnard star. We recovered the rotation period. It's one of the best fit ever for the rotation period with a GP. So you see a modulation of 153 days and error bars that are well below 1 Kelvin, around 0.5 Kelvin. And you see the rotational modulation. One advantage compared to other techniques, such as V sin I changes, is that this star, the V sin I, the geometric one, is super small. It's about 80 meters per second. So you're not seeing a widening or breathing of line profiles. You're really seeing correlated depth changes. So as an activity tracer, so there's a paper by Claire Moutou with one candidate and one Robusta planet published with Spirou. And you have a planet at 24 days. And of course, if you see planets, you may see spot stars, the rotating stars. And of course, Claire did her job and she double checked that we were not seeing the rotation of the star. And it's something that anyone should do with Spirou data, basically. And if you, it's the top one, it's two stars, I'm just showing one. You absolutely want to check that there's no period there at exactly that, basically that the period that we get from some temperature changes. And here's an example of the detail for that star, for which there's a planet, and she used a GP train on the detail to remove activity in the data in a radial velocity. So it's not just that you see that the period is the wrong one. You also detrain your data to find planets using the temperature. So you're seeing spots, you're seeing inhibition of convection, and you can remove these effects from your data and get the planets. Just for fun, and that's the last effect I want to mention, we saw in Spiro data an equivalent of the Rossiter effect in temperature, which is really weird. So you have a star with spots, okay? And you hide a bit of a star. If you hide the middle of your star, there's limb darkening. The star appears cooler. And then you go to the limb and you hide a bit of the limb, it appears hotter. Can we see it? Of course we can. Here's HD 189733. It's like the most famous algebra transiting, one of the most famous. And you see baseline, it's a five Spiro time series. So you see the baseline temperature, you see the error bars are well within, the bin error bars well within 1 Kelvin. And you see an increase in the early transit, so the orange here, line, then a decrease and an increase and a decrease. And it's basically the temperature shadow of the planet on the star. And you can fit it, you can rederive the impact parameter. Okay, the uncertainties on the impact parameter are bad compared to what people do with photometry, but still you recover a reasonable impact parameter. And we call this a Fox effect. So once you've seen the Fox effect there, you cannot unsee it. It's a little ears and a nose. So now you're awake. So, so you say, oh my God, do I need to code all of this myself? It must be a nightmare to code. No, we did it for you. We're nice. So there's this temperature activity indicator is a byproduct of the line-by-line velocity measurement. So you go on the website of the line-by-line project, and you click here, 5, and the explanation, and you basically give any time series to Spiro, and you give it to the code, and it computes the temp for you. Okay, so you do not need to recode it yourself. And getting to the end. So it's fully implemented in the LBL framework. Any time series with Montéal will give you a DTEM sequence. Okay. So we already coded for Spiro, Sophie, when you see the list here, not yet Espadon. We have to sit and do it. It's on our to-do list. The DTEM, the derivative spectra are defined in the Harps domain and in the Spiro domain, so we will need to recreate Espadon. That's what we're singing. Part of the red, that's okay. No bad. We just need to sit and do it, but it's in our to-do list. Yeah, that's it.
Thank you very much. Questions?
If I have some learned
Okay, so there are things.
Can you repeat the question?
Yeah. How would you handle basically continuum normalization in hotter stars? There's something I did not say. There are lots of things I did not say, okay, that are under the carpet. And the spectra here are high passed. Okay. So you need to select a scale below which or above which, depending on which way you will want to look at it, you assume that there is no feature. So you high pass on, I think it's 500 kilometers per second in our case. You will need to select a scale. You will need to create a library also of spectra of varying temperature. The temperature of your spectra that go in does not need to be known very well, because if you have two stars spaced by 1,000 Kelvin, even if you have temperatures to 200 Kelvin, you don't mind. You know the gradient more or less. It works. So you need spectra, a series, not rotating ideally. You can broaden them, but ideally you would start with non-rotating stars and broaden them, and you need to select a scale. But let's see, we could do it. It's a little project in itself, but it's not horribly hard.
Yeah. Thank you very much.
But it's there, right? You do not need to recode it.
Not the same. So, sure, beyond that, you can fly a file. But if you call that, so
Yes.
we need to have our thing for a file. We can just log in from Zolly install here.
Yep.
So I can just what now go bags by letters. So if I could be working in the bands.
Okay. That's another one. So, okay, remember, this is done for every single pixel. So we actually bunch them per line. So basically domains between two consecutive maxima. So having a minimum. So it's actually computed on every single pixel in your spectrum. Okay, in the end. So so I showed it for one pixel, but there's a weighted sum, a weighted sum over the entire domain, but slightly fancier than a weighted sum. There's some rejection of outliers and so on. But yeah.
Can you work in this new file?
No, but yeah. Okay. You basically say your star, your M4, looks 10 minus 3 like, so it's an M4 plus 10 minus 3 of an M5, basically. So you're describing your star as changing in temperature bulk, which is not necessarily true. So you know, cut me if I go over time. When you do the limb darkening, okay, and you naively, you always start naive in these projects, you naively say, oh, it's just a brightness ratio. It does not work because you're probing elsewhere in the atmosphere. So I actually to predict the flux, so it was wrong. I literally got the wrong values, and the reason was that you're probing higher up and not equivalent to just a colder star. So the edge of the edge, that's a K dwarf, by the way. The limb of a K dwarf is not exactly an M0. It's my God, let's get this. So the edge of a mid K, let's say, so the limb on the side has an effective brightness of, let's say, an M0, let's say. But it does not have exactly the same spectrum because you're looking at higher up, you're not looking at the same gravity, you're not at the same place in lines. So you actually need to project to do the detail. So basically, you redo the error you would assume in the LBL. Otherwise, you don't get the right depth. Yeah. So it's a little more subtle when you don't get in true temperature changes, but like probing the limb, it's first order, it's a temperature change, but not really.
Other questions? Anybody out in Zoom?